For lecture 4, we're going to talk about conjugated systems. We're going to spend some time looking at orbitals again, and we're going to look at how orbitals can interact with each other in more complicated systems. The subtitle of this chapter is, Why is benzene so special? This is the question that we're going to try to answer by looking at this material. If you know about benzene, you probably know that it's an interesting structure, has some interesting properties. If you don't know about benzene yet, that's fine. Hopefully you'll be fairly familiar with it by the time we finish this chapter. So I want to begin with our first organic reaction. I want to look at hydrogenation for a moment here. This is a hydrogenation reaction where we have a double bond called an alkene that reacts with hydrogen gas in the presence of a palladium on carbon catalyst. Sometimes you might see a platinum catalyst. It's basically the same functionality. But the result of this reaction is that the alkene is reduced to a regular alkane. What you'll notice is that each carbon that is participating in the double bond in the reactant only has one hydrogen in the reactant state. This carbon has one hydrogen, this carbon has one hydrogen. In the product, both of those carbons have two hydrogens. This guy's got two, and this guy's got two. So in this reaction, the hydrogenation, we are adding one hydrogen atom to each carbon that was participating in the double bond. We are doing that essentially by splitting the H2 molecule in half and putting one hydrogen on each of the double bonded carbons. This table below here comes out of Wikipedia, and what they're showing you here are the molar heats of hydrogenation for different types of starting material. So heats of hydrogenation will be changes in heat or changes in enthalpy that result from converting an alkene into the alkane. This table is sorted by degree of substitution. So I want to talk about what degree of substitution is. Basically, degree of substitution is the number of carbon atoms that are attached to the double bonded carbons. So if we look at ethylene, here are the double bonded carbons. There are no carbons attached to those carbons. It's just the two hydrogens. So we would call that an unsubstituted alkene. 1-butene has one carbon attached to the double bonded carbons. Now, there are two carbons here, but only one of them is actually attached to the double bonded carbon. So we call that monosubstituted. There is one substituent on the double bonded carbons. Trans-2-butene, which is the same structure that we used in the example, is disubstituted. It has two substituents, this carbon right here attached to the left double bonded carbon, and this carbon right here attached to the right double bonded carbon. We have a tri-substituted alkene where we have 1, 2, 3 carbons attached to the double bonded carbons, and tetrasubstituted would be 4 carbons attached. 1, 2, 3, 4. So what you'll notice is that as you increase the number of substituents from 0 to 4, you decrease the molar heat of hydrogenation. That means that there is less energy being released when we transform that double bond into a single bond. What that means is that the double bond is getting more stable. The more substituents that we put around the double bond, the lower its energy, the less energy that it contains that can be released when we get rid of it. So I want to show you this in a graphical form here. Here we have a di-substituted alkene where we have 1, 2 carbons attached to the double bonded carbons, and the heat of hydrogenation for a di-substituted alkene would be 27.6 kcal. We saw that in the previous slide, 27.6 kcal for a disubstituted alkene. Here's a monosubstituted alkene. Now, again, since this is less substituted, it's going to be higher in energy or higher in enthalpy, and more heat will be released when we hydrogenate that. So if we convert that double bond into a single bond, we get to the same product that we did for the disubstituted reaction. We get to this same product, but we will have released more energy, 30.1 kcal. Interestingly, if we look at a molecule with two monosubstituted double bonds, you'll notice that the energy of hydrogenation is exactly double what it would be for one monosubstituted double bond. What that means is, in this case, the two double bonds, their energies are additive. If you have one, it takes 30.1 kcal to hydrogenate it. If you have two, it takes 60.2 kcal to hydrogenate it. So let's look at another example. Here we have another molecule with two double bonds. One of them is monosubstituted, which should have a heat of hydrogenation of 30.1 kcal. And the other double bond is disubstituted, so it should have a heat of hydrogenation of 27.6 kcal. That means that the total heat of hydrogenation for both of these double bonds combined should be 57.7 kcal. But in reality, it's 53.7 kcal. This molecule is more stable than it should be by 4 kcal of energy. This pattern, double bond, single bond, double bond, single bond, that alternating double single pattern is called conjugation. And this is evidence that conjugation is a stabilizing factor. For some reason, and we'll talk about why in a few minutes, but for now, for some reason, these bonds together are more stable than they would be if they were separate. You'll notice that previously, these double bonds are not conjugated. They are, in fact, in a sense, isolated from one another. We don't have a double single pattern. We have double single double. So if they are isolated from another, they have energies that are additive. But if they are conjugated with one another, double single, their energies are not quite additive. They are more stable than the sum of their parts. And we're going to look at why that is. Here's another example of a molecule that has also a monosubstituted double bond. This double bond right here only has one carbon attached to it, and a disubstituted double bond. This double bond right here has one carbon attached to it and a second carbon attached to it. So also, again, this double bond, I guess you could say, has two individual double bonds that should add up to an energy of 57.7 kcal. But in reality, in this case, it adds up to nearly 70 kcal, which is destabilized by 12.1. So this pattern where you have two double bonds that lie exactly next to each other, not separated by any single bonds, but directly next to each other, that's called cumulation. And cumulation is a destabilizing factor. So let's look at what's going on here. Like I promised, we're going to be looking at orbitals and using the interaction of the orbitals to understand why these are more or less stable. So what we're talking about in these molecules is really the pi system. When we're looking at the double bonds, remember that double bonds form by side-to-side overlap of pi orbitals, of p orbitals. So these pi bonds are really all that's changing. The sigma system, the overlap of the hybridized orbitals, is not really playing a factor here. So we're going to be looking at everything exclusively from the picture of the pi system. So here's the simplest carbon-carbon double bond. This is ethylene. This was the first structure in our table over here, ethylene. 2 carbons double bonded with hydrogens on both carbons. This is also called ethylene. Both carbons on ethylene, notice, are sp2 hybridized. They have 3 bonds being made in the sigma system from its hybrids, and then an unhybridized p orbital on each carbon that are overlapping to make the pi bond. And each carbon contributes 1 electron into that pi bond. So here's a picture. This should look somewhat familiar to you. This is the molecular orbital picture of the pi system. Again, we're kind of ignoring the sigma system, just looking at the pi system. If we have 1 p orbital from the carbon on the left and 1 p orbital from the carbon on the right, 2 orbitals mixing should produce 2 new orbitals. We can get a bonding orbital where the 2 orbitals are mixing in phase, where the positive lobes are overlapping with each other and the negative lobes are overlapping with each other. That's constructive overlap, and that gets us a pi bond, what we see here. Here's another picture, another representation of what the orbitals look like. The other way that the orbitals can mix, instead of mixing in phase with one another, is they can mix out of phase with one another. So the positive lobe of one is mixing with the negative lobe of another, and as you remember, when we overlap or mix 2 waves in opposite phases, they cancel each other out. So we end up with a region in space between those atoms where there was no electron density. That's called an antibonding orbital. We call it pi star. So this should look familiar. This is basically what we looked at in the sigma case. We were overlapping s orbitals, for example, but it looks the same kind of setup for a pi system. We have 2 orbitals now, the bonding orbital lower, the antibonding orbital higher, and 1 electron from each of the original pi electrons are donated into each other, and they get to fill into the lower energy orbital. That means that we have 2 electrons sitting in the bonding orbital. They get to behave according to these pictures here, and so they are allowed to exist kind of in a pi system between the 2 atoms. Let's look at a conjugated system now. Here's a molecule called 1,3-butadiene. You don't need to understand at this point what the name comes from or where the name comes from. We'll talk about that more specifics when we learn more about these double bonded systems. But for now, this is called 1,3-butadiene, and you'll notice that it is conjugated. We have a double bond, then a single bond, then a double bond, that alternating double, single, double pattern. Again, all 4 carbons in 1,3-butadiene are sp2 hybridized. Every one is involved in a double bond, and every one has 3 atoms attached to it. If you figure out where the hydrogens go, you'll see that each carbon has 3 atoms attached, which means it should be sp2 hybridized. Again, each carbon contributes 1 electron into its pi bond, and therefore we have 4 electrons in the pi system total. 2 electrons in one bond, 2 electrons in another bond, 4 total, 1 from each carbon. So if we were to look at only the pi system, we could look at the molecule like this. Just look at the 4 carbons in a row and kind of highlight their p orbitals. To simplify this even more, we represent it like this, where we have just a straight line to represent the chain of carbons, carbon 1, carbon 2, carbon 3, carbon 4, and each of those carbons has a p orbital. Since this is a planar molecule, every single one of these carbons is sp2 hybridized, means that they're planar. We can also assume that the p orbitals are also planar with each other. And again, they have to be planar to be making the pi bonds in the first place. So here we've got 4 carbons, each with its own p orbital, and they're all lined up next to each other. So if these guys are going to mix, we're going to be mixing 4 orbitals, and therefore we should be producing 4 new orbitals. Basically, there should be 4 ways in which these 4 orbitals can mix. I want to point something out real quick before we jump into this. In this picture here, we have overlapping between carbon 1 and carbon 2. The p orbitals are overlapping between carbon 1 and carbon 2 to get us the pi bond. So we have overlapping between carbon 1 and carbon 2. That's great. We also have overlapping between carbon 3 and carbon 4. That gets us a pi bond between carbon 3 and carbon 4. So 1 and 2 are overlapping, 3 and 4 are overlapping, but you'll notice that there is no pi overlap between carbons 2 and 3. So a good question to ask would be, why are we getting overlap between carbons 1 and 2 and between carbon 3 and 4, but not between carbon 2 and 3? There must be some reason for that. So let's look. When we're going to mix 4 orbitals together, we should produce 4 new orbitals. So the first molecular orbital that we're going to get is going to be the one in which all of the p orbitals are mixing in phase. So positive lobe, positive lobe, positive, positive lobe, negative lobe, negative lobe, negative lobe, negative lobe. So we have bonding interaction between all 4 orbitals. That is the lowest energy arrangement, where all waves are mixing in phase. This also means that there is electron density between all the carbons in all the pi orbitals. So we basically have pi bond character, pi bonding interaction between 1 and 2. We also have pi bonding between 2 and 3. And we also have pi bonding between 3 and 4. Now, that's not exactly what this picture looks like, right? This says we should have bonding between 1 and 2 and 3 and 4, but not between 2 and 3. So this picture gets us part of the way to what our structure looks like, but it's not the entire picture. All right, I'm going to move this up. So here's our first molecular orbital where we had all bonding interactions. No nodes. Notice we have no anti-bonding interaction. So our second arrangement of these orbitals, we're going to go from no nodes, from 0 nodes to 1 node. And just to maintain as much symmetry as possible, the node goes right in the middle. So how could we arrange these orbitals so that we have 1 node right in the middle? Well, we'd have to have bonding interaction or in-phase interaction between 1 and 2. And we need to have bonding interaction between 3 and 4. But we need to have anti-bonding interaction between 2 and 3. So we're going to have to flip the phases of these waves. So we're going to have positive lobe, and then negative lobe, negative lobe. That gets us electron density in the pi system in the terminal phase. We are allowed to have pi bonding between 1 and 2. We're allowed to have pi bonding between 3 and 4, but we're not allowed to have pi bonding between 2 and 3. So that actually, molecular orbital 2, looks a little bit more, in fact, it looks exactly like what this structure says it should look like. Bond between 1 and 2, no bond between 2 and 3, and then a bond between 3 and 4 in the pi system. Okay, so that's a better picture. Let's keep going. This is only 2 of the ways that these waves can mix. Remember that we need to get 4 because we mixed 4 in the first place. All right, here's our third molecular orbital. We're going to have, instead of 1 node, we're going to go up to 2 nodes now. So we need to have 2 nodes, and again, we're going to try to maintain as much symmetry as possible. So the best way to have 2 nodes with a completely symmetrical picture would be to have to have a node between carbons 1 and 2, then have bonding interaction between 2 and 3, and then have no bonding, so anti-bonding interaction between 3 and 4. That gets us a node there and a node there with bonding interaction between 2 and 3. Notice that this doesn't look anything like what our structure was. In fact, it almost looks like it's the opposite of what our structure was. Whereas our structure had bonding between 2 and 3, bonding between 1 and 2, and bonding between 3 and 4, with no bonding between 2 and 3. Here we have no bonding between 1 and 2, no bonding between 3 and 4, but we do have bonding between 2 and 3. All right, so that's our 2-node picture, molecular orbital number 3. Molecular orbital number 4 should have 3 nodes. So the only way that you can have 3 nodes is to have anti-bonding interactions between all pairs. So no bonding between 1 and 2, out of phase. No bonding between 2 and 3, out of phase. And then no bonding between 3 and 4, out of phase. So all of our pairs are out of phase. If we arrange this in terms of energy, this is what these two diagrams look like. Here's the picture from ethylene. Remember, we had a single bonding orbital where the lobes were in phase, and then we had a single anti-bonding orbital where the lobes were out of phase. So 2 orbitals, and they were above and below in energy from where the isolated p orbital was. So this is just showing us on this diagram where the energy would be for an isolated p orbital. Anything below that energy is more stable, and anything above that energy is less stable. So for ethylene, the bonding orbital was more stable, the antibonding orbital was less stable. And remember, since each orbital, each lobe, we should say, each individual p orbital, donated 1 electron into the system, we have 2 electrons right here, and they get to fill into the bottom orbital. For 1,3-butadiene, we had 4 orbitals. Pi1, the molecular orbital 1, had them all in phase. Molecular orbital 2 had them in phase between 1 and 2, in phase between 3 and 4, but out of phase between 2 and 3, so 1 node. Then we went to 2 nodes, and then to 3 nodes. So you'll notice that the 0 node and 1 node representation are lower in energy than the unmixed system, and the 2 node and 3 node orbitals were higher in energy than the isolated system, not the unmixed system. Now remember, since we had 4 carbons, each one contributing an orbital, each one contributing 1 electron, we have 4 electrons that we get to fill in. So those 4 electrons are going to fill again from bottom to top. So we're going to have 2 in the lowest orbital and then 2 in the next highest. You'll notice that in both of these pictures, we have electrons only in the lower energy orbitals. We have no electrons sitting in the higher energy orbitals, which means that for both of these pictures, the electrons get to go down in energy as a result of the molecules forming, as a result of that pi system forming by overlapping these p orbitals. Now, think about these orbitals as a set of instructions that tell the electrons where they get to exist. For example, this bottom orbital, pi1, says that you can have electrons mixing between all 4 of these orbitals, kind of moving between carbon 1, carbon 2, carbon 2 and carbon 3, and carbon 3 and carbon 4. So these 2 electrons get to move between all 4 of the carbons. They get to spread out amongst all these atoms, all 4 regions, or all 3 regions in space between them as well. That's why they're low in energy, because they get to spread out amongst the largest area. The pair of electrons in molecular orbital 2, the one node picture, these guys get to exist in the space between carbon 1 and carbon 2, and they also get to exist in the space between carbon 3 and carbon 4, but they don't get to exist in the space between carbon 2 and 3. So again, we are restricting their movement a little bit more, therefore their energy is going to be a little bit higher. So this pi system that contains 4 electrons, really the 4 electrons are behaving in different ways. 2 of them are moving amongst all 4 of the atoms, and the other 2 are moving amongst only the first, second, and the third and the fourth. Let me show you how the orbital picture actually does match our understanding of the structure in reality. So here is our structure. We've got 1,3-butadiene like that. Now, we could imagine a resonance structure where what I'm going to do is I'm going to take a pi orbital and move it there, and this guy and move it there. We could also move the electrons in the other direction, but we basically get the same structure, just a mirror. So that picture gets us a resonance structure that looks like this. We'd have a lone pair there, the negative charge, and we'd have a positive charge there. Now, based on what we know about resonance, remember that the real picture of the molecule is one where you take all the resonance structures and you combine them all together with more influence from the more stable structure and less influence from the less stable structures. So let's do that. Here's our pi system, and I'm gonna just, well, we'll draw it like a normal line angle here. There's our 4 carbons. Now, the structure on the right is less stable than the structure on the left. So we should have less contribution from that, but still some contribution. We can't ignore it completely. It is a valid structure, and so it should contribute to reality. But the structure on the left is a better picture. So let's give our structure on the left more weight. So we've got more pi bonding between 1 and 2, and more pi bonding between 3 and 4. But then we still have, again, contribution from our minor structure. We should have a little bit of pi bonding character between carbon 2 and 3. Now, that should be our resonance picture. According to resonance, that's what our structure should look like in real life. Let's go back to our orbital picture, though. Remember that our orbital picture says that our 4 electrons are behaving according to 2 different sets of instructions. One of those sets of instructions, remember, had all the lobes in phase. So we'll do this. We'll have all the lobes in phase. Meaning that we've got pi bonding between carbons 1 and carbon 2, between carbon 2 and carbon 3, and between carbon 3 and carbon 4. That's pi bonding character according to our first orbital. That was molecular orbital 1. molecular orbital number 1. What was molecular orbital number 2? Well, it had one node. So molecular orbital number 2 with one node should look like this. We're going to have in phase for our first pair, out of phase for our second pair, and then in phase for our third pair. So according to molecular orbital number 2, where's our pi bonding? It's pi bonding between 1 and 2, pi bonding between 3 and 4, pi and pi. So if we combine these two pictures, if we imagine overlapping them together, okay, let's just do this. We'll put them right underneath one another. Where do we have most of our bonding? We have most of our pi character between carbon 1 and 2 and between carbons 3 and 4. We have contribution of pi bonding or contribution towards the pi bonding occurring from both of those orbitals. Both of those orbitals contribute. We also, though, have a little bit additional contribution right there between carbons 2 and 3. That matches our picture. The green area is getting us our pi character where we have our pi bonds. But our orange area gives us a little bit of additional pi character there. So really, the notion that resonance gives us, that we've got more pi contribution from our structure on the left and less pi contribution from structure on the right, also matches the molecular orbital picture, which says that we have more contribution from pi bonds between 1 and 2 and 3 and 4, and a little bit of contribution from pi bond between 2 and 3. This is benzene. Benzene is a very interesting structure. It's a 6-membered ring with alternating double and single bonds. So here's one picture of benzene, double bond, single bond, double bond, single bond, double bond, single bond. It's a conjugated system, but it's also a cyclic conjugated system, which is different from 1,3-butadiene, which was conjugated but not cyclic. It was linear. Now, there are really two ways to represent benzene. Because it's circular, because it's a ring, we could have the double bond starting here and going single, double, single, double, single. Or we could have the double bond starting here and go double, single, double, single, double, single. Now, these two resonance structures are equivalent. They are exactly the same. There's no way you could say one is higher in energy than the other. They should both be identical. So the real picture should have equal contribution from both of them, where basically, instead of having a double bond here or a single bond there, we have 1.5 bonds. And instead of having a single bond here and a double bond there, we should have 1.5 bonds. So you can see we should have 1.5 bonds in every position. We represent that with this structure, since it's not really realistic to envision the double bonds being in one place, one physical location, but not the other physical location. They should be in all the locations, but spread out so that they're not really full double bonds, but 1.5 bonds. We just draw this circle around the ring, saying, okay, there's pi density all around this ring. And we need to just understand that it's not full double bonds. They're 1.5 bonds. That would be that combined representation of benzene. Now, in 1,3-butadiene, a double bond would be 1.34 angstroms, and a single bond would be about 1.48 angstroms. These are not pure double bond lengths. Remember that a regular carbon single bond was about 1.54 angstroms. A regular carbon double bond is about 1.2 angstroms. So this double bond is a little bit longer than it should be. It's a little bit more single bond like. And remember that according to our picture of resonance in 1,3-butadiene, that bond between carbon 1 and 2 is double bonded in one picture, but it's single bonded in the other picture. So it's more double bond like, less single bond like, but it's not a pure double bond. Same thing for the single bond. The single bond is more single bond like, less double bond like. Again, the iPad picture we had more contribution as a single bond than it did as a double bond. So it should be more single bond like, but it's not a pure single bond either. So those bond lengths, again, since they're not true double bonds or not true single bonds, we have data, we have experimental data that tells us exactly what those lengths are, and that confirms that there's something interesting going on in 1,3-butadiene to make these not pure double or single bonds. The same is true for benzene, but you see that it's even more extreme. These bonds are all the same length. They're all equal. Additionally, not only are they all equal, but they're all exactly between what a double bond and a single bond should look like, 1.397 angstroms. So even more contribution now. Another way to view this would be the orbital picture of benzene. So remember that each of these carbons in benzene should be sp2 hybridized. That's why each one gets to make a pi bond with its neighbor. But again, we can't really say that that one neighbor is always pi bonding, because in one picture we have pi bonding, in another picture we have single bonding. So these electrons are really moving around this ring. There's an overlap between all the orbitals, orbital 1 to orbital 2, orbital 2 to orbital 3, orbital 3 to orbital 4, etc. And we have movement of electrons around this ring. This means that the conjugated system, the conjugated nature of benzene, allows the electrons to move around the ring and cover as much space as possible, to be smeared out as much as possible. This means that these pi bonds are not really normal pi bonds. They're not normal double bonds. In fact, the pi bonds in benzene are generally unreactive towards normal pi bond reactions. So we're going to learn more about double bond reactions in the future, and we're going to learn specifically about benzene reactions in the future. But for now, I want you to know that these double bonds are not normal double bonds. And the reason they're not normal is because their locations are constantly moving. The electrons are not stuck between two atoms like a normal double bond would be. They get to move around all the atoms, and that makes their behavior fundamentally different. So let's try to look at a molecular orbital picture of benzene. Remember, when we combined these orbitals for ethylene and for 1,3-butadiene, we combined them in such a way that we produced as many new molecular orbitals as atomic orbitals that we started with. So in benzene, if we are mixing 6 orbitals together, we have one orbital from each carbon, and they're all mixing. One mixes with 2, 2 mixes with 3, 3 mixes with 4. And so in that sense, 1 gets to mix with 2, and 1 gets to mix with 3, 1 gets to mix with 4. They all get to mix. So for mixing 6 orbitals together, we should be producing 6 new molecular orbitals. This is what that picture looks like. This is the molecular orbital picture of benzene. It's actually quite a bit different than the molecular orbital picture of 1,3-butadiene and ethylene. One thing that it does have in common is that it has one arrangement of these orbitals where we have all bonding interaction. That's the lowest energy arrangement. There are 0 nodes in this picture, where we have all the positive lobes oriented above the ring, for example, and all the negative lobes oriented below the ring, for example. That would be the one and only way that you can have all bonding interaction. But remember that we had one node as a higher energy orbital. In benzene, there's actually two ways to have a single node. You could have a single node going right down the middle, kind of vertically. This picture on the left, our node is going vertically. But we can also have one node going horizontally, kind of slicing right through those end carbons. So we now have two ways to have a perfectly symmetrical picture with one node. So these should be equal in energy. They both have one node. So we're going to have, say, all bonding on the left side here and all bonding on the right side here, but then anti-bonding between the left side and the right side. So there's our node. We can also have bonding, say, on the back side here and bonding on the front side here, and then a node cutting the back side off from the front side. We can go higher energy again, from 0 node to 1 node, up to 2 nodes now. Now, again, there's two ways to have 2 nodes. You can have 2 nodes cutting the ring vertically and horizontally, like we have here on the left, but we can also cut the ring diagonally to have 2 nodes. Lastly, we can have 3 nodes, where we have a node essentially between every orbital in every plane. So everything is out of phase here. We have all anti-bonding interactions. This is a very different picture. Now, we still have one electron being contributed into this picture from each carbon. Each carbon is contributing a p orbital, and each p orbital comes with 1 electron. So if we have 6 orbitals and 6 electrons to fill into those 6 orbitals, where are the electrons going to go? Well, we're going to be able to put 2 electrons in the lowest orbital, and then we're going to fill the next 2 orbitals according to Hund's rule. So we're going to go 1 electron in the bottom, 2 electron in the bottom. Then we're going to go 1 electron here, 1 electron here, and then we're going to go opposite spin, 1 electron back in the left and 1 electron back in the right. So that means that the bottom 3 orbitals, remember the bottom half of the system was below the energy of the non-bonded electrons. So if we had this picture here, we had the bottom half of the diagram was lower in energy than the isolated orbital, and the top half of the diagram was higher in energy than the isolated orbital. For benzene, we end up with that same picture. We end up with all of our electrons, all 6 of our electrons, in these bottom 3 orbitals, and no electrons in the top 3. So as a result of mixing these orbitals, all of the electrons get to go down in energy. They all get to exist in the bottom half of this diagram. That's the picture of benzene. Let's keep going. I want to show you a couple other examples. Let's look at 1,3-cyclobutadiene. That's this structure here. It looks a lot like benzene in that it's a cyclic system with alternating double and single bonds. So it too is conjugated. It's just like benzene, but we have 4 carbons instead of 6. Again, all the carbons should be sp2 hybridized. They all have 3 atoms attached to them with 1 unhybridized p orbital to make that double bonds. So if we're going to be combining in this pi system 4 carbons, each with its own p orbital, and each p orbital with 1 electron, we should be combining 4 orbitals. We should be making 4 new orbitals. This diagram is what those 4 orbitals look like. Again, we've got one picture, one arrangement of these orbitals where they are all bonding. We have 0 nodes. Okay, all of the orbitals are in phase. All of these lobes are in phase. We can go higher in energy to give ourselves 1 node. We can have that node, okay, slicing kind of vertically through the ring here or horizontally through the ring here. Both of those are equivalent because they are 1 node orbitals. Again, it just turns out that in one of these, the bonding is on the left side and the right side, and in the other one, the bonding is on the top side. They say the back side and the front side, maybe. But they're both equivalent. They both have 1 node. Then we can go higher and we have a 2 node picture where we have all of our orbitals, all of our lobes out of phase. Now, again, we're mixing 1 electron from each of the 4 carbons. So we've got 4 electrons to fill in here. Notice how these electrons are going to fill in, though. We can still put 2 electrons in the bottom half. 2 electrons in the bottom half. But when we go up to the next level, we have to follow Hund's rule. So we're going to put our next electron, say, into the left picture, and then our 4th electron into the right picture. We have a dramatically different scenario here. First of all, let's think about where the orbitals are relative to the non-bonding orbital. Remember that in this picture here, the energy of the non-bonding orbital cut right through the middle of the diagram. Everything on the above it was higher in energy. Everything below it was lower in energy. But we basically cut the diagram right through the middle. That's what we did with benzene. Cut everything right down the middle. That's the energy right here of the non-bonding orbital. And all of our electrons were below that in energy. With 1,3-butadiene, it's a very different picture. Because the middle of the orbital, or the middle of the diagram, is right here. These 2 orbitals, the 1 node orbital picture, both of these arrangements are actually at the same energy of the non-bonded orbital, meaning that any electrons that sit in these orbitals don't get to go down in energy. They maintain the same energy as they would have had they not been bonded. Let's simplify this picture a little bit. Here was benzene. Remember, benzene had 1 orbital there. We had 2 orbitals that were higher. We had 2 more orbitals that were higher again. And we had a last, or 6th orbital, that was the highest. And the non-bonding line kind of goes right through the middle. There's our non-bonding line. And for benzene, we had 6 electrons that we got to fill in. We got to fill 1, 2, 3, 4, 5, 6. That was benzene. All of the electrons are below, all the electrons are lower in energy than they would have been had the orbitals not mixed together. But in 1,3-butadiene, in cyclobutadiene, it looks a lot different. We had 1 orbital that was low, we had 2 orbitals that were higher, and we had a 4th orbital that was even higher. And in this case, the 2 orbitals that cut right through the middle of the diagram are going to sit right at that non-bonding line. So our 4 electrons, again, we only have 4 this time, they're going to fill in like this. So they're going to go one there, but then they'll go one there and one there, meaning that these electrons that are sitting in those orbitals are not a bond. Those are not bonded or not bonding. They're not bonding. 1,3-butadiene, then, cyclobutadiene, should not look like the picture that was on our slide. It has one bond. That bond is somewhere. It's that bond right there. It's somewhere on the ring. But then on our other carbons, we have unpaired electrons, meaning 1,3-butadiene should actually exist as a radical, as a diradical, this 1,3-cyclobutadiene. It doesn't really exist like the picture here on the slide. So that picture that I used, this simplified picture, is sometimes called the polygon trick. Kind of depends on what text you're using. I was always taught it as the polygon trick. These are also called Mobius diagrams. But there's a trick that you can use to predict the orbital arrangement of the molecular orbitals in a cyclic conjugated system. So remember, benzene, we had one orbital that was low, two degenerate orbitals that were higher, two more degenerate orbitals that were higher still, and one orbital that at the very highest, the fully non-bonded, fully anti-bonding picture. Cyclobutadiene, we had one orbital that was low in energy, two degenerate orbitals that were higher in energy and equal to the non-bonded orbital in energy. They were right on that non-bonding line. And then we had a higher orbital still. Here's cyclooctatetraene. This is 8. Okay, you'll notice that 8 electrons. If we're going to mix 8 carbons, we're going to have 8 electrons, and we're going to have 8 orbitals. They look like this. 1 at the very lowest. We have 2 degenerate orbitals that are below the non-bonding line. We end up with 2 degenerate orbitals at the non-bonded line, 2 degenerate orbitals above the non-bonding line, and a fully non-bonding or anti-bonding orbital at the very top. What this says, it says the molecular orbital energy diagram of a completely conjugated, regular cyclic system, so a pentagon, a hexagon, octagon, a heptagon, something like that, has the same polygonal shape as the compound itself, always with one with one vertex, then all bonding molecular orbital being at the bottom. So you'll notice that the shape of this diagram looks like benzene. The shape of this diagram looks like cyclobutadiene. And the shape of this diagram looks like cyclooctatetraene, the 8 carbon ring. And the non-bonding line cuts directly through the horizontal center of the polygon. You can use the polygon trick as a quick way to assess the stability of a structure like this. By looking at the way these electrons fill into these orbitals, you could see that benzene should be very stable. All of benzene's electrons are paired up, meaning they're bonding, and they are all lower in energy than they would have been if they had not mixed in the first place. So benzene should be very stable, and that is exactly what we know to be true. But this also tells us that cyclobutadiene and cyclooctatetraene should exist as diradicals. They should be not stable. There's no reason that these electrons should ever be thought of as being involved in a pi bond. They are absolutely not being involved in a pi bond. Just because I can draw it like cyclobutadiene I did here, but draw it and say, oh, it's just like benzene. it's really not like benzene at all. It really has a very different arrangement. So this is called aromaticity. Everything that we've been talking about, comparing benzene being good to these other structures being particularly bad, is part of a concept called aromaticity. So aromaticity is a set of conditions that need to be met in order for the molecule to be particularly stable, like benzene does. The first part, the first point, the first requirement, you could say, of aromaticity is that the structure must be cyclic. Like we've seen, we've been doing cyclic structures, and containing some number of conjugated pi bonds. It doesn't have to be conjugated around the total structure. We'll see some examples, but it needs to have some number of conjugated pi bonds. Every single atom in the ring needs to have an unhybridized p orbital, and this is normally the case where the ring atoms are going to be sp2 hybridized. If all of your ring atoms are sp2 hybridized, then all of the atoms will have an unhybridized p orbital on them. Thirdly, those unhybridized p orbitals must be able to overlap to form a continuous ring of parallel orbitals, like this picture of benzene here, where all of these rings, all of these orbitals in the ring were overlapping because they were parallel. That's a third requirement for aromaticity. The structure need to be planar or very nearly planar for that overlap to be effective. I'll show you an example towards the end of the lecture of an example where something would be hybridized this way, sp2, but then not planar. The fourth condition of aromaticity is what we've just seen in the previous diagrams, that there must be no unpaired pi electrons. And that condition, whether there will be unpaired electrons or there will not be unpaired electrons, like we've seen, is related to the molecular orbital symmetry. Is the diagram symmetrical through the center of the diagram or not? Do we have orbitals sitting at that non-bonding line? So if a molecule meets all four of these conditions, we say the molecule is aromatic, or it has the property of aromaticity. And that conditions, those conditions, are associated with extraordinary stability. And they also end up being susceptible to certain types of reactions that other molecules are not. Well, again, we'll talk about these reactions more later in the course. But as long as they meet all these four conditions, we can call them aromatic, and they all kind of have these special properties associated with them. If a molecule meets the first three conditions, so it's cyclic, containing conjugated pi bonds, they're all unhybridized p orbitals on every carbon, and so the orbitals are overlapping in a planar ring, but there are unpaired electrons. So if the three conditions are met, but the fourth is not met, we call it anti-aromatic. An anti-aromatic compound is one that meets the first three conditions, but not the fourth. And it turns out that anti-aromatic molecules are unusually unstable. They give rise to structures that are so unstable that they don't really exist. For example, cyclobutadiene. This structure does not really exist. If it does exist, like we saw, it should exist as a diradical, which is remarkably unstable. So that's aromaticity. There's a shortcut to get there, though. We can use a rule called Huckel's rule, developed by Eric Huckel, as a shortcut for predicting which cyclic rings, which are called annulenes, and similar compounds, are aromatic or are not aromatic or anti-aromatic. So once we've met all of the criteria for the first three, So again, our question is, are they aromatic or are they anti-aromatic? If they're anti-aromatic or aromatic, they're going to meet the first three conditions. But how can we tell whether they're going to have unpaired electrons? Well, of course, we could always go back and look at the polygon trick, draw out a Mobius diagram, count up all the electrons in the structure, and fill them into this pi system and tell if they're going to have, that way, if they're all going to be paired like they are with benzene, or if we're going to end up with unpaired electrons like with cyclobutadiene or cyclooctatetraene. But there's a slightly easier way, and that is called the 4n plus 2 rule. That's Huckel's rule. It says that if the number of pi electrons in the cyclic system is 4n plus 2, where n can be any integer. So n can be 0, 1, 2, 3, etc. If that makes 4n plus 2, the system is aromatic. So for example, benzene. We know benzene is aromatic. We've seen that. It's cyclic, it's conjugated, it's planar, and we have no unpaired electrons. There are 6 electrons in the system, and 6 electrons is 4n plus 2 if n is 1. N is 1, 4n plus 2 makes 6. So a system with 6 electrons will be aromatic, 4n plus 2. If, however, we only have 4n electrons, not 4n plus 2, but 4n, then the system will be anti-aromatic. So looking at cyclobutadiene or cyclooctatetraene, cyclobutadiene has 4 electrons. Cyclooctatetraene has 8 electrons. 4 and 8 meet the 4n plus 2 condition. So we can expect that because they have 4n number of electrons, that they will be anti-aromatic. We don't necessarily need to draw out the polygon Mobius diagram to figure that out. So the types of systems that will be aromatic will be, say, 6, 10. If n is 2, that makes 10, right? If n is 3, that makes 14, 12 plus 2. So 6, 10, 14, 18, etc., 22. If your cyclic system has that number of electrons, you can expect it to be aromatic. If it's 4n, so if it's 4, 8, 12, 16, 20, you can expect your system to be anti-aromatic. If you think about what's going on here, why Huckel's rule works, you can look at this diagram. Here we have a energy diagram where we have the one low energy orbital, and then we have these degenerate orbitals as far up as we go, and then eventually we're going to have one orbital at the very top. The vacant orbitals aren't being shown. So for example, benzene has 1 at the bottom, and then 2, and then 2, and then 1, etc. That's what we have here. We have 1, and then 2, and then 2, and then 1. Whether these are filled or not, they're just showing the vacant, they're hiding the vacant orbitals. So if we have 4n plus 2, the 4n are always going to be paired up in these degenerate orbitals. The plus 2 are always going to kind of fill into these bottom orbitals. So mathematically, if you're going to do the accounting, the 2 are on the bottom, and 4n will always fill up the degenerate orbitals. We're going to add another 4 electrons for every level of these degenerate orbitals, n number of filled orbitals. But if instead we have 4n plus 2, but we take away those 2 electrons, so instead of 4n plus 2, we have 4n, the electrons that we're going to take away from our diagram are going to be the 2 electrons at the highest level. Remember, we're never going to take 2 electrons from the low energy orbitals. We're going to remove electrons from the high energy orbitals. So anytime you have 4n and not 4n plus 2, you're going to be missing those 2 electrons that are going to be needed to fill those highest orbitals. It's the n number of shells, but we're missing those extra 2 electrons. That would be up here. Let's look at kind of a special example of aromaticity. This molecule is called furan, and let's analyze furan from the perspective of its orbitals and figure out whether it's going to be aromatic, anti-aromatic, or non-aromatic. So in furan, the first thing, or I guess for any structure, the first thing that we're going to want to do is identify where the p orbitals are. The first requirement, remember, that we need is that we have a cyclic, fully conjugated system. Well, we definitely have a cyclic system. This is a 5-membered ring where 4 of those are carbons and 1 of them is an oxygen. Again, this is called furan. So let's go through and identify the hybridization of all of these atoms. Let's start on the left. The carbon right there, that is sp2 hybridized. It's got 3 bonds connected to it. You can check, or 3 atoms connected to it. We've got the oxygen, we've got the other carbon, and we've got a hydrogen right there. So it's got 3 atoms connected to it. So it should be sp2 hybridized. If it's sp2 hybridized, that means it's got a p orbital. So I'm going to draw the p orbital in there. The next carbon, right there, should also be sp2 hybridized. Looks exactly the same. This carbon, also sp2 hybridized. And this carbon, also sp2 hybridized. So as far as these 4 carbons are concerned, all of these orbitals can overlap. But in order for it to be aromatic, we have to have a fully cyclic and fully conjugated system. So what is the hybridization of the oxygen? Remember that for oxygen, with 2 bonds, it also has 2 lone pairs. The hybridization for that oxygen should be, according to Vesper theory and according to everything that we learned about hybridization theory, with 4 electron domains around it, should be sp3 hybridized. Well, okay, if it's sp3 hybridized, that means that there are no p orbitals, which means that we cannot have an aromatic system from furan. However, here's an exception to the rule. The oxygen in furan is actually sp2 hybridized. It's not sp3 hybridized, as you may have thought. Here's why. Oxygen, if it turns sp2 hybridized, would have its orbitals arranged like this. We'd have sp2 making that sigma bond, sp2 making that sigma bond. We'd have sp2 containing 1 of the lone pairs, but then we would have an unhybridized p orbital, which I'll make in green. And that unhybridized p orbital could contain the other lone pair. Like that. If that oxygen does that, what it needs to do is it needs to absorb an energetic penalty. Remember that if it were sp3, both lone pairs would be sitting in an sp3 orbital. They would be sitting in an orbital that contains 25% s character. But when it rehybridizes to be sp2, it has to move 1 of those lone pairs into an unhybridized p orbital, a p orbital with 0 s character. So those electrons move up in energy, and that's generally a bad thing. That's why oxygen generally would not be sp2 hybridized unless it absolutely had to be. So why does it choose to be sp hybridized now instead of being sp3 hybridized? Well, notice what happens when this becomes sp2 hybridized. We now have a system that is fully conjugated. We have overlap amongst every atom with its p orbitals. We now have a fully cyclic conjugated system. Every single atom contains that p orbital. In addition, let's count up how many electrons are in the pi system. We've got 2 electrons in that pi bond, 2 electrons in that pi bond, plus the 2 electrons that we just relocated into the new p orbital on oxygen. That's 6 pi electrons, which is 4n plus 2, which means that furan is aromatic. Oxygen absorbs an energetic penalty and moves its sp3 hybridized electrons into an unhybridized p orbital. But the result is that the entire molecule now gets to become aromatic. That by moving those electrons into a p orbital, they actually get delocalized around the ring along with these other electrons. These electrons are moving throughout the entire ring system because it has this kind of racetrack created by the p orbitals. That's pretty cool. Oxygen on furan is not sp3 hybridized like you might expect. Let's look at another example. Let's look at pyrrole. Similar structure. And again, we're going to go through a similar process to determine whether this is aromatic, anti-aromatic, or non-aromatic. What did we do before? We looked at each carbon and we tried to determine where the p orbitals were. Well, again, we've got a p orbital on that sp2 carbon, a p orbital on that sp2 carbon, a p orbital on that sp2 carbon, and a p orbital on that sp2 carbon. Great. That's 4 p orbitals. We have a conjugated system, but it's not fully cyclic. We don't have that complete racetrack yet. Let's look at nitrogen. Remember that nitrogen with 3 bonds should have a lone pair on it. So there's our lone pair. And again, based on what we know from Vesper theory and hybridization theory, that nitrogen should be sp3 hybridized. However, if that nitrogen were sp3 hybridized, this molecule would not be aromatic. It would not have that complete cyclic system that we need. So notice what nitrogen can do though. Just like with oxygen, nitrogen can rehybridize to be sp2. If it does that, it can use one of those sp2 orbitals for that bond, one of the sp2 orbitals for that bond, and its third sp2 orbital for the bond to hydrogen, which is right there. That leaves an unhybridized p orbital left over into which we can put both of the electrons. So lone pair goes into the p orbital. So again, we now have that pi system where all the p orbitals can mix. Carbon 1 can mix with carbon 2, carbon 2 can mix with carbon 3, carbon 3 can mix with carbon 4, carbon 4 can mix with nitrogens, and nitrogens can mix with carbon 1. So we get this racetrack again. We have a completely cyclic conjugated system. And how many electrons do we have in that pi system? Again, we've got 2 from the double bond there, 2 from the double bond there, and 2 from the lone pair. That's 4n plus 2. It's 6 pi electrons. So this guy, pyrrole, is also aromatic. The nitrogen on pyrrole is actually planar. It's not trigonal pyramidal like most nitrogens that you would expect with 3 bonds. Most nitrogens with 3 bonds like this would be trigonal pyramidal, but it's actually planar, and it maintains its planarity in order to maintain the aromaticity. Everything kind of gets to hold on to each other by remaining flat. We'll look at a couple other examples here. Here are 3 cyclopentadienes. Again, don't worry about the names for now, but let's think about the arrangement of the atoms and electrons in all 3 of these. In the first structure, there are 2 hydrogens. In the second structure, there's only 1 hydrogen, right? Remember that carbon with a positive charge has 3 bonds with no lone pairs. And the structure on the right, same thing. We've got 1 hydrogen, except that carbon with a negative charge is 3 bonds with a lone pair. So let's figure out what the hybridization of these guys must be. Carbon with 4 bonds, it's got to be sp3. We don't have any options there. So if our orbitals look like this, p orbital there, p orbital there, p orbital there, p orbital there, there's nothing we can do to make this last carbon have a p orbital. Those electrons are already bonded. They're going to be sp3. Remember that we make a hybrid for every bond that we have. We do not make bonds with we do not make sigma bonds, I should say, with unhybridized orbitals. They're always being made with the hybrids. So this guy cannot be aromatic. He also can't be anti-aromatic. So we just say he's non-aromatic. Non-aromatic. All right, let's look at the cation. Similar picture. Again, we've got the p orbitals in the same places that we saw in furan and pyrrole. What is the hybridization on that carbon? It's got 3 bonds, which means that it should be sp2. It doesn't need to rehybridize or anything. It's already sp2, which is great because that gives it a p orbital. However, even though we've got this fully conjugated system being sp2, how many pi electrons are there? There's only the 2 double bonds. We don't have any electrons to put into that last p orbital. It's a cation, so it's missing an octet. So we only have 4 pi electrons, which means that it's anti-aromatic. It's actually very unstable. that molecule is unstable, just like any other anti-aromatic molecule. We can expect that it would have unpaired electrons. It'd exist as a diradical, meaning that even though we drew two bonds there, they don't really exist as two bonds. They exist as one bond and diradical. All right, let's look at the next structure. Again, the p orbitals are in the same place. There, there, and there. What should the hybridization be on that carbon? It's got 4 electron domains, right? It's got the bond to the carbon, bond to the other carbon, bond to the hydrogen, plus the lone pair. 4 electron domains should be sp3, but hopefully you're picking up on the pattern here. One of those electron domains is a lone pair, meaning that that carbon can rehybridize. If it rehybridizes to sp2, and that becomes a p orbital, we can get that racetrack. We now have every single carbon has an sp2 orbital on it. That was also true for our anti-aromatic structure. Don't forget, that was still there. In this case, instead of having 4 pi electrons, we have 6 again. 6 pi electrons, which is 4n plus 2. So that guy is aromatic. It's going to be more stable than we would expect. Now, this is kind of interesting because in this case, in this context, the anion, the carbanion, is more stable than the carbocation. And that's usually not the case. Usually the carbanions are less stable. Carbon is not particularly electronegative, so it doesn't really like negative charges. It is usually much more happy with positive charges. But this changes the narrative. The fact that the anion can be aromatic gives it a ton of stability. And the fact that the cation is anti-aromatic means that it loses a lot of stability. Here's a picture from your book for the 3 structures we just worked through. Here's the Mobius diagram for cyclopentadiene, this 5-membered ring. Again, we've got a cyclic ring, so the 5 orbitals that we get from mixing should be in a 5-membered ring, a pentagon, with the single all bonding arrangement on the bottom with all the orbitals in phase. The question then becomes, how many electrons fill in? With the cation, we only have 4 electrons. So we end up with an unpaired system. It's going to be anti-aromatic. For the anion, we've got 6 electrons in our system. The 4 from the double bonds plus the 2 in the lone pair. So we're going to add 2 electrons to our system from that, going from the cation to the anion. We can add 2 electrons to our system. That gives us 6 electrons. So that would be aromatic. Let's look at what happens with additional heterocyclic atoms. We already looked at pyrrole. Remember, in pyrrole, this nitrogen needs to be sp2 in order for our system to be aromatic. And because it can be aromatic, nitrogen will absorb that energetic penalty, move its electrons into that higher energy orbital to allow the overall state of the system to become lower. In pyridine, we actually don't need that to happen. Notice that in pyridine, we've already got 6 electrons in the pi system. We've got a double bond there, and a double bond there, meaning that these electrons on nitrogen do not need to be in a p orbital in order to make the system aromatic. In fact, if it were to somehow make its way into a p orbital, this would be anti-aromatic. It would have 8 pi electrons if those were in the pi system. So actually keeping these electrons out of the pi system is good for the stability of the system. In pyridine, these electrons sit in a sp2 hybrid. That nitrogen, since it's already making a pi bond, should be sp2, and it should be already using that p orbital to make the double bond. So these electrons cannot sit in the p orbital. They need to sit in an sp2 orbital. That keeps them out of the system. Notice that the sp2 orbital is perpendicular to the p orbital. You should remember that from our sp2 hybrid picture. It stays out of the pi system. So very different behavior, right? Between pyrrole, those electrons on the nitrogen are in the pi system. They are required to be there for the molecule to maintain its aromaticity. In pyridine, it's the opposite. These electrons need to sit out of the pi system in order to maintain the aromaticity. This also plays a role in reactivity. For example, pyrrole is not basic at all. These electrons are not reactive. They would never be used to, say, make a bond to an H+, for example, or be donated to some other species to make a bond, like in a Lewis base. Why? Because they're actually not really on that nitrogen. They're being spread out around this entire system. They are not available for reaction. They're being occupied by the ring in order to maintain the aromaticity. In pyridine, on the other hand, these electrons are free and ready to be reacted. Pyridine is quite basic. It does not matter whether these electrons are sitting as a lone pair on nitrogen or whether they are bonded to something to nitrogen. Either way, this ring still is able to maintain 6 electrons in a conjugated system from the pi bonds. We do not need those electrons, so they are free to react. So pyridine, very basic. Pyrrole, not basic at all. The question is just, what is the role of the electrons? If the electrons are required for the molecule to be aromatic in the first place, they're going to be non-reactive. Otherwise, they will be reactive like normally. I want to make one more note here about cyclooctatetraene. This is one of the structures that we alluded to earlier in the chapter. It was one of the molecules that we first saw was anti-aromatic. The structure looks like this. We've got an 8-membered ring. It's conjugated. So we have alternating single and double bonds, and it's completely conjugated, which means that we have a complete racetrack in our pi system. If we set up the Mobius diagram, we would see that we have 3 orbitals below the non-bonding line. One of them is the lowest orbital, the all bonding configuration. We've got 2 degenerate orbitals on the non-bonding line, and then we've got the 3 orbitals at the top. Filling in those orbitals with 8 electrons, we have all 6 of the lowest orbitals paired up in their electrons, and we have the degenerate orbitals at the non-bonding line with unpaired electrons. Again, that is the trademark of an anti-aromatic molecule. One of the requirements for aromaticity or anti-aromaticity is that the molecule be planar. And so far, we've accepted that these molecules be planar because they are sp2 hybridized around the ring. But I want to show you an example where cyclooctatetraene kind of breaks that rule. As drawn here, all of the double bonds in cyclooctatetraene are cis. Hopefully you remember what cis double bonds look like. But basically they're the double bonds that kind of curl around the double bonds so that it kind of makes a U shape. As drawn on the left here, all the double bonds are cis. But there's another version of cyclooctatetraene where two of the double bonds are cis. The cis double bonds are here and here. But two of the double bonds are trans. You'll see that these double bonds kind of zigzag right there and right there. Their geometries are different. That is allowed only in rings with 8 or more members in the ring. So cyclooctatetraene has 8 members in the ring. So you're allowed to have trans double bonds in a ring. Just to show you why you can't have trans double bonds in rings that are smaller than 8. If we just look at benzene, normal benzene has 3 double bonds and they're all cis. That one's cis, that one's cis, and that one's cis. That's what you would expect for a ring that's smaller than 8. If we try to make a trans double bond, make a zigzag type double bond in a ring of 6, there's no way to connect those ends. It doesn't work. It's not allowed. But if you've got 8 or more, you basically have enough additional atoms to connect the ends of the trans double bonds. So that's allowed for cyclooctatetraene. And that's actually pretty important because you'll notice that in the trans version of cyclooctatetraene, the trans double bonds actually cause the ring to kind of pop out of plane. Well, look here. The area where the trans double bonds exist in this ring cause the ring to pop out of plane so that one half of the ring up here is on one plane, and this half of the ring down here is on another plane. And what we end up with is a region where the orbitals cannot overlap. We don't get overlap there, which means that we can't have an aromatic system, nor can we have an anti-aromatic system. So having an anti-aromatic system is really, really bad. So rather than having the cyclooctatetraene be completely planar, like it would be if all the double bonds were cis right here, if that were the case, it would be anti-aromatic, and that would be very bad. So to avoid that, the ring actually pops out of plane. It can either do so by actually forming trans double bonds, or even in the cis version, like you see here, all these double bonds are cis. They kind of make a U shape. There's a U shape. There's a U shape. There's a U shape. And there's a U shape. They're all cis, but you can see that they are not planar. And again, the reason for it to be, say, motivated to pop out of plane is to avoid actually being anti-aromatic. If those orbitals don't overlap, then the Mobius diagram doesn't really exist. And so we can't have an anti-aromatic arrangement. So that's the end of lecture 4. Our workshop from the Stramanis workbook is chapter 17. You can skip model 4.